In this video, we'll explain how the MAP sensor works. This sensor plays a key role in determining engine load and calculating how much fuel to inject. To understand how it does this, we first need to understand what's happening inside the intake manifold. When a piston moves downward during the intake stroke, it tries to fill the cylinder with air. To do that, the air must pass through the throttle body and the intake manifold before reaching the cylinder. When the throttle is partially closed, the airflow is restricted. The pistons continue trying to draw in air, but the air cannot flow in freely. As a result, the pressure inside the intake manifold decreases. The more closed the throttle is, the greater this pressure drop usually becomes. On the other hand, when the driver presses the accelerator and the throttle opens, air can enter more easily. As a result, the pressure inside the manifold increases. This means that simply by measuring the pressure inside the intake manifold, it's already possible to estimate the engine load. And that's exactly what the MAP sensor is for. Many people believe that the MAP sensor measures how much air enters the engine, but in reality, it measures neither airflow nor air mass. The only thing it measures is pressure. The sensor is connected to the intake manifold and is constantly exposed to the pressure changes occurring inside it. The question is, how does it convert those pressure changes into an electrical signal? Inside the sensor, we find a small port that transmits the manifold pressure to a silicon diaphragm. Above the diaphragm is a sealed chamber containing a reference pressure. When the manifold pressure changes, the pressure difference between the two sides causes the diaphragm to flex slightly. The deformation is extremely small. However, built into the diaphragm are piezoresistive elements. These elements change their electrical resistance when subjected to mechanical deformation. As the pressure inside the manifold increases, the diaphragm flexes in one direction. When the pressure decreases, it flexes in the opposite direction. Although this movement is almost imperceptible, it is enough to deform the piezoresistive elements integrated into the diaphragm. And when these elements deform, their electrical resistance changes. Of course, the ECU cannot measure that resistance directly. Instead, the sensor uses those resistance changes to modify its output signal. To do this, it contains a small electronic circuit powered by the ECU itself. As the resistance of the piezoresistive elements changes, the electrical behavior of the circuit changes as well. As a result, the sensor's output voltage increases or decreases depending on the pressure inside the intake manifold. The ECU continuously receives the voltage generated by the MAP sensor. From that voltage, it can determine the pressure inside the intake manifold. If the pressure is low, it knows there is a high vacuum. If the pressure increases, it knows the vacuum is decreasing. This allows the ECU to indirectly determine the engine load. But one important question still remains. Why does knowing the pressure make it possible to determine how much air is entering the engine? The MAP sensor's primary function is to help estimate the amount of air entering the engine. Many systems do this using a strategy known as speed density. In this method, the ECU combines three main pieces of information: the manifold pressure provided by the MAP sensor, the intake air temperature, and the engine speed. Using this information, it can estimate the air density inside the intake manifold and calculate approximately how much air mass is entering the cylinders. Based on that calculation, it determines how much fuel to inject in order to maintain the proper air-fuel mixture. Let's look at a few examples. With the engine off, there is no vacuum being created by the pistons. As a result, the pressure inside the intake manifold is nearly equal to atmospheric pressure. At idle, the throttle is only slightly open. The pistons continue drawing in air, creating a significant vacuum. The pressure measured by the MAP sensor decreases. The throttle opens much wider. The pressure inside the manifold increases, and the MAP sensor's signal immediately reflects that change. At full load, the manifold pressure can get very close to atmospheric pressure. On the other hand, during certain deceleration conditions, the vacuum can become even greater than it is at idle. Each of these conditions produces a different sensor reading. To summarize, the MAP sensor allows the ECU to determine what's happening inside the engine by measuring only the pressure inside the intake manifold. It does this using a tiny silicon diaphragm capable of detecting extremely small pressure changes. Its internal electronics convert those pressure changes into an electrical signal. The ECU then uses that information to estimate the mass of air entering the engine. Finally, once it knows the mass of the incoming air, it can calculate how much fuel to inject. And that concludes our explanation of the MAP sensor. Don't forget to leave a comment with the systems or components you'd like us to explain in future videos. Thanks for watching.